foundation, right? So it will be faster to do the design because you only use one profile. But that's only good if your soil condition is relatively uniform. So but if your soil condition vary considerably, across the project, then typically you cannot use generalized soil profile. What you typically use is you use the foundation specific soil data. So for example, if this is the location of your pile, you drill a hole next to it and you use the data from that hole to design your foundation for that foundation. That's so you have to do, so in this case, you have to do a lot of soil boring or CPT close to all the foundation. So you use that specific soil data that you get from next to the foundation to do that, to design that foundation. For example, if you have 10 foundation, then probably you need 10 soil boring, each boring for each foundation. Yeah, so you can design it that way. That obviously will cost more and will take more time to the design, but that's I think that's the way to go. That's the preferred way to go if your soil varies significantly across your project. It show you the typical boring log and what we call it stick log. So basically you plot all the CPT and soil boring along your bridge. So you'll be able to see how the soil vary from point to point. So this is a typical plot that we typically plot for our subsurface for our project. So, and also one thing to add to, typically what you want to you should have a minimum of, you should have a soil data a minimum of approximately 6 meters below your pile tip. So if your pile go to 100 meters, you want to have a soil data at least 106 meters. If your pile is 100 meters, if your soil data is only 50 meters, that is no use because you don't have anything below. You don't have anything to design your pile below 50 meters. So your data have to be approximately 6 meters below your design pile tip. Again, this is showing example about this is showing example about the Blocon N60 Blocon when we plotted with elevation on depth. That. So this is all the Blocon that we get from different soil boring. There's so many of them we plotted together. I don't know. You sometimes you might want to group it section by section. Sometimes you want to combine all of them. So this is that example, and this is another example of friction angle. You can estimate friction angle from the Blocon. So and then you plot them with depth. So again, this showing a lot of variation here, and this is another example of shear velocity. That we measure directly in CPT, or we interpret it or estimate it from the cone data, showing you the variation of velocity with depth. Oops. As you can see, this obviously there's a lot of scatter here. The data are scattered significantly. So when you use this plot, have to be used with caution. There's so many uncertainty in terms of the Blocon and the friction angle. So a typical soil profile. This is the typical. This is general soil profile. Again, as I say, if your soil is uniform, you probably can live with a profile for all your foundation. So this is one example here that we have 5 soil layers. So layer 1, 2, 3, 4, and 5. And layer 1 is loose to medium sand. Layer 2 is medium to dense sand. Layer 3 is clay, and so on. 5 is clay, and then you list the depth. This is from 0 to 20 feet and 20, 45 feet. Also list elevation and all these parameters. The average Blocon within this layer, the average friction angle, modulus, and other parameters that you use for your design. So this is just showing a typical table for generalized soil profile. So again, as I say, pile design can use the generalized or idealized soil profile. all supported, right? All supported specific soil data, right? As I say, depending on the variability of your soil data. Okay, those so that I covered about the typical investigation, how you characterize the site for design. So before I continue with the design methodologies, is there any question? Try to finish it in 1 hour or at least 1 and 15 minutes. Question? Okay, so the design methodology that I'm going to present is based on ASTO 2020 LRFD based design specification. So LRFD is a load resistant factor design, right? It's different than allowable soil, allowable stress design, but it's very similar concept. But this is what we call LRFD. The design philosophy of LRFD is based on limit state. Limit state is that considers limit state that consider deformation and stability. Okay, so there are 3 limit states in ASTO. Again, ASTO is the code that we use here for bridge. Right? ASCE 7, that is the code that you use for building. So ASTO is similar to ASCE, but specifically developed for bridges. Okay, so there are 3 limit states for ASTO. One is the surface limit state. It basically, it will limit the stresses, deformation, and crack. That. So this limit state will tell you what is the maximum stress that you cannot go above it. What is the maximum deformation? What is the maximum crack? Thing like that. So mainly for service, operational, mainly depending for operational, state. Second one is the strength limit state. Is basically is a design to ensure stability against local and global value. That make sure that the whole thing do not, topple or slide or collapse. That. And the third one is the extreme limit state. Is basically, you want to make sure that your bridge will not collapse, during earthquake, during flooding, when truck hit your bridge or something like that, vehicle collision and other usual loading, So there are 3 limit states that we need to design our pile and our foundation for. I will go this quickly, that basically, it's very simple concept that this is the load. All your load, all the combination of your load have to be less than your resistance. Right? To be able to, your structure will be safe if your resistance is more than load. Right? That's just, it's common sense. Right? So again, Q is the load, life load, death load, earthquake load, flood load, wind load, any type of load. Right? And gamma is the load factor. So this is the factor that you apply for different type of load, like life load, maybe 1.2, death load maybe 1.1, so different load factor for different load. And this is another factor to convert that consider ductility, redundancy, operation, different thing, That so when all of them, the multiplication of all of these for all the load is basically a combined load or total load that your pile need to resist, need to carry. So this is the loading side and this is the resistance side. Rn is the nominal resistance, so or ultimate resistance. We call it nominal resistance, and phi is the resistance factor that you apply to the nominal load. The multiplication of these two is called factor resistance. So basically, ASTO saying that your factor resistance have to be bigger than the factor load. That's just common sense. Your load have to be smaller than your resistance to be able to have a stable foundation. So the equation is very simple. The total bearing capacity of pile is divided into two. It's from the tip resistance of the pile tip, and the side resistance, resistance along the pile. So the the summation of the two give you the total pile capacity, right? So this one, the T is the tip resistance factor. The AT is the area of the drill shaft, right? The QT is the unit tip resistance, tip or base resistance. And then the same thing with this one, AS is the sub area, summation of the area of the pile. S is the unit sub resistance, and VS is the sub resistance factor, right? The factor here. They have a different load factor and different resistance factor for different component of your resistance. So equation is very simple and intuitive, right? There's nothing to see about it. So I note that the load factor and resistance factor were estimated or were determined based on statistics. They did statistical analysis, and based on the statistical analysis, they come up with this load factor and resistance factor. So this factor, basically, as I say, is estimated based on the real world data, based on the practice. So because of that, this factor vary, right, for different country or different region, depending on the local design and construction practice, right? So the practice or design and practice in Indonesia might be different than what we have. Thing like that, So that I will just make sure that when you do the design, you just don't borrow it from anywhere. You need to use your local practice. So load and resistance factor, these are the two, right? The load factor for various loading and weight are typically greater than one. They're less than one, but most of them are one. You want to be more conservative, right? So you want to design your pile based on bigger load than smaller load. So the loading combination, live plus death plus earthquake, different combination. I'm not going to go into it, but if you're interested, you can see this table from different load combination and different load factor they need to use for those combination. Right? And resistance factor, depending on the type of soil and the methods of analysis, and also resistance type, they're all different, but typically they are less than one. Again, it's for conservative, right? Because your resistance, you wanted your resistance to be less than what you think is correct, right? To be safe, right? So, and you can also look at resistance factor table, this table from ASTO. I'm not going to show it here. And different resistance, this is for sat resistance in compression, and this is for base resistance or tip resistance, and also depending on the soil type. If you have a cohesive soil or sandy soil, the resistance factor is 0.55, and if your soil is cohesive soil is 0.45, and for base resistance, you 0.4. So different soil, different resistance have a different load factor. You need to go to this table to get a complete list of the resistance factors. Actually, if you think about it, resistance factor is almost the same. It's equivalent to the safety factor in allowable stress design. It's just if your resistance factor is 0.55, what does that mean? What is your factor of safety? It'd be 1 over 0.55, right? Which is approximately 2. So if your resistance factor is 0.4, that's almost the same with having a factor of safety of 1 over 0.4, which is 2.5. So it's basically the same logic. It's just put it different way, you know. So I just show you quickly the equation that we typically use. This is for axial capacity for cohesive soil, for clay and silt. And typically we use total stress, right, for clay. So this is the equation that we use for tip resistance. So the QT, which is the unit resistance, tip resistance, is the NC times SU. SU is the shear strength. That the NC is, you can estimate based on this equation, which is a function of okay. So SU here is the undrained shear strength of the clay. C is the penetration depth, you know, the depth of the pile, and D is the diameter of the pile or the shaft, right? And typically you don't want to go more than 80 KSF, you know. The code limits you to 80 KSF, no more than that. So, and then for side resistance, it's the same thing, very simple equation. Alpha times SU is your undrained shear strength, and alpha you can compute it based on this equation. That you can see that for small SU you have alpha 0.55, but for larger SU, then you reduce it by this factor, right? So alpha will be less than 0.55. So as you can see, this is very simple equation, nothing magic about it, you know. It's very simple. So again, this PA is atmospheric pressure. So SU divided. So this is the dimensionless quantity, right? So again, you know, the equation is very simple, but the key factor here is, you know, how do you estimate the SU, right? Because this is the key, right? And that's not easy, right? Because as I showed you before, sometimes there's a lot of variation. So selecting one single value for your design sometimes could be very difficult. So you need to, you know, look at, you know, or assess the impact of selecting your value to your design, right? And also it's mostly based on experience. If you have a long experience, for example, dealing with soil in Jakarta, so you know approximately, you know, the SU for clay is like this, you know. So you don't want to go, you don't want to use anything that is very different than what you're understanding based on your experience. So the key here is how to select SU. And again, the equation is very simple. So this is another equation for axial capacity, but this one is on the this one is for the cohesionless soil, for sand or gravel. So again, the equation is quite simple. You know, you just, this is the unit side resistance is basically beta times the effective vertical stress, and beta is you know can be computed using this equation, which is the function of friction angle, right? The shear strength. So beta is basically a function of friction angle and the sigma p. So beta is what is called load transfer coefficient. Sigma v is the effective vertical stress. Phi is the effective friction angle, and sigma p is the pre-consolidation stress. You can estimate beta directly from friction angle, but ASTO also give you alternative. Instead of estimated from friction angle, you can estimate the friction angle based on N160 blow count, SPT blow count, right? And then you can also get the sigma p based on this equation. And the value of C and M, you know, listed here, depending on whether you have sand or clay or gravel, you know, different time. And one thing I want to point out that N60, as I told you before, is the SPT value adjusted for 60% energy. Again, you cannot use the N value that you measure directly from the field to use for this equation. You have to adjust it for 60%. N160 is the same thing, and it's the same energy, except you need to do another adjustment based on the overburden stress. Okay, you can go to the ASTO and get the equation that you can use this one, but N160 again is the 60% blow count, and N160 is a 60% blow count adjusted for vertical confining, effective confining pressure. That's the friction angle, right? This is the subfriction, right? And the equation for tape resistance is even simpler, right? It's only 1.2 and 60. But the code limits you to use N60 no more than 50, or the QT should be no more than 60 KSF. That unless you can justify by pilot test, which we're going to discuss that. Right? So if you can justify based on the test, you can use higher value. Other than that, you are limited to only 60 KSF. Okay. Again, as the other one, the equation is very simple. The key here is how do you estimate your N and phi and phi angle. Right? This is the key because, as I said, sometimes there's a lot of variation, but you need to choose one value that you think is appropriate. Right? So for various soil and wall conditions. Right? Typically, for power design, I think I'm running out of time, so I need to go faster, or I may skip something. Typically, for geotechnical engineer, you are given this table called foundation load table, right? So the bridge engineer or the structure engineer will give you, okay, this is the load that you need to design your pile for, right? Remember, we have 3 steps, right? So they will give us the load for surface limit, the load per pile, right? So this is different bands, so different load here for surface limit. They will also give you the load for strength limit, right? This is compression, this is the maximum load, and there's no a little bit of tension here and a little bit of lateral here. And then they also give you, the load for extreme limit, right? The same thing under the extreme limit, what is the maximum compression, what is the maximum tension, and what is the lateral. Okay, so this is a table that you typically get from the bridge engineer. So pile capacity, right? So you have a pile or a drill shaft, and you have a load here. You need to design your pile. So typically, this is what you get using the equation that I just showed you before. You can plot this, right? You can plot basically the tip resistance or sud resistance with depth or with elevation with depth. That's showing, for example, this one is for toe resistance, right? So the blue line. So the dotted line is the nominal resistance, and the solid line is there for factor resistance for the toe. Same thing with these two. These are for sud resistance. So this is for, the red one is for compression, and this one is for tension resistance. Right? So when you sum them up, when you sum the toe and sud, what you get is a total resistance. Right? This black line. So this is your pile capacity as a function of elevation or depth. Right? So, for example, I want to know what is my pile length if my design load is 10,000 kips. So you just draw a line here. Right? And then draw a line so you know, okay, this will be my pile length, right? For 110, 110, or is it 118 to approximately here. So this is my pile length, right? You need 10,000. You need 1,500, you need more. If you need only 5,000, it will be less, right? So you can use this curve to basically estimate the pile length that you need for axial load. Right? And for lateral, the same thing, right? You have a pile, you put a load here, lateral load. And for lateral, typically you represent the soil using soil spring, right? You put a spring here, the PY spring for your lateral load. So the same thing, what we do here is, we compute the pile length and the pile head deflection. So the length of the pile and the pile head deflection, right? So if the pile is 20 feet long, the pile deflection is 1.4. As you increase your pile length, the deflection will go down, right? The pile head will go down, right? Because the longer pile will be more stable. But up to a certain point, that there will be no more reduction in pile deflection. So this is going to be your design pile length, right? So at this point, there will be no significant increase in pile deflection. So this will be basically your design pile length. So my design pile length for lateral load in this case is 38 feet. So this is the minimum pile length for lateral load. So 38. You have a pile length for axial load. Now you have the minimum pile length that you need for lateral load. And then, again, typically for you need to analyze the forces and the pile too. So you have a lateral load, you have soil spring up. So you can compute the load, the deflection profile on the pile, and also the bending and shear. Right? There are 4 loading cases here. So basically, we force the pile top to move 0.25, 0.5, 75, 1 inch. Right? So, and you can compute the bending moment and shear along the pile. Right? So this is typically we use program called LPAL to do this. And for structural design of the pile, you basically have a table like this. This is apartment 1, apartment 28, the type of the pile, and you consider fixed head, pile and cap connection is fixed head, and this is the loading cases. You specify the deflection of the pile head 0.25 to 1, and you compute the average shear and then the maximum bending and shear. Right? So this is the pile group reduction or pile multiplier. I don't know you're aware or not. When you have a group of pile, your capacity go down, right? So this is what we call P multiplier, to basically to account for the group reduction. Right? And you can use this, basically you use this to design your rebar of your pile. Right? You know maximum moment, maximum shear. You use that value to design your rebar or reinforcement. And also sometimes you have a pretty thick pile cap and you want to use the pile cap to help you for lateral resistance. So these are the typical passive resistance that we use for the pile cap, depending on how much deflection that you expect. So it gives you this one, to give you the deflection, and the passive resistance is passive resistance, right? And also the stiffness of the pile cap. So typically, if the pile cap is pretty thick, like for example, 2 meter or 1 meter pile cap, you don't want to ignore it, right? Because it will help you constrain the lateral movement. Okay, when you finish everything, do all the axial loading, lateral loading, what your end product is what is called pile data table. Basically, this table is showing you, the design of your pile. For example, okay, this one is on bend number 20, right? This is 11-foot CID, 11-foot drill shaft, and you specify the cut-off elevation, what elevation you want to cut the pile, right? And then also let's use some of the loading that is being used to design the pile. And I just want to show you this one, right? This column, if you look at this, see this number here. This is the depth elevation for different loading. For example, this one, the first one, A1. A1 is the I can't read it here. Okay, A1 is basically for compression. So basically, you list all your design depth elevation for different loading for compression, tension. This one is A2 is what? A2 is compression but extreme loading. A1 is compression for strength limit, and C is for settlement. So you check the settlement of the pile. So this is the required depth elevation to meet your settlement criteria. No more than half an inch or no more than 1 inch. And you also list the elevation or pile length, the minimum that you require for lateral load. So when you list all of them, so your design pile elevation will be the longest pile, right? Or in terms of the elevation will be the smaller. Right? For example, for bend 20, my design type elevation will be 140.4 or 140, right? Because if you construct your pile to 140, then you will meet all other criteria, right? So this is the minimum pile length that you require for different loading, and you typically select the one that is the longest, right? Okay. So this is the end product. Okay, if you are geotechnical engineering, this is the one that you're going to give back to the structural engineer. Okay, this is my design of the pile. So you need to build the pile according to this table, and you can pay, I guess, after you give them the table. Okay, so okay, just let me share something. Sometimes when you build a bridge, okay, this is the apartment. Remember, apartment 28, we have a group pile group here, right? And this is the approach embankment, the approach embankment into the bridge. Ideally, you want to construct this embankment first, right? And let the embankment settle. When the settlement is done, the embankment no longer settle, then you build the wall and the pile, right? So the pile will not be subject to downdraft, right? That's the ideal sequence of construction. But sometimes that takes a long time because the settlement of the embankment could take days or even months or even years. Right? So you can use the big drain to speed up the settlement, but that will cost you money. So typically the contractor doesn't like to do this. What they want is they want to build the wall first and the pile first. When they finish that, and then they build the embankment. The problem with that one is obviously is faster, right? You don't need to wait for settlement. But the problem when you do that is the settlement will settle, right? The embankment will settle, right? Because of settlement, then you will induce downdraft force on the pile. Right? Because you will induce some force on the pile because of the settlement. And that downdraft will induce settlement. The pile will settle. It will add the axial force on the pile, right? Because the pile will subject to downdraft or greater axial force. So you need to check the structural capacity, right? Make sure that your pile have enough capacity to take this downdraft. Yeah. So if we do that, then you need to check that. One way to do it is what we did is we build a 3D model for the embankment, settlement model for the embankment. So this is the embankment. This is the location of pile, approximately location of pile, and this one gives you the contour of the settlement of the embankment with time. Right? So this is basically the location of the pile that you want to estimate. How much the pile will settle due to the embankment settlement. So what you need to know is the pile top deflection. Right? How much the top of the pile will deflect. Subject to the embankment settlement. So based on the neutral plane theory, you can Google it. This guy Philemius, he said as the pile top settlement is equal to the soil settlement at neutral plane plus the elastic shortening of the pile above the neutral plane. Right? So the pile settlement is equal to the soil settlement at neutral plane plus elastic shortening. So what we did is, basically we draw this load curve. We started with depth load, right? Because the depth is always there. At that point, there will be no live load because no vehicle running on the bridge. So only depth load, and the load will increase, right? Because of the skin friction downdraft, right? So as you go deeper into the pile, the axial load will increase, right? Because of the downdraft, so it will increase it. And then on the other hand, you have this blue line, where is resistance. You started with tip resistance, and then as you go up from the tip of the pile, the resistance will be more, right? Because you pick up some skin resistance, right? And so the resistance will go up as you go up to the ground, and the load will increase as you go down to the ground. So when the two curves intersect, this is the neutral plane. This is what we call the neutral plane. The plane where the load is balanced, right? There's no up, no down. So this is the neutral plane. And from this graph you can tell, my neutral plane is at elevation 105. approximately 205 feet, my neutral plane. So you know the elevation, then you go to this curve. This is the curve of settlement and elevation at the location of the pile. Right? So you know this, the settlement will be 0 at the bottom, right? And settlement will be more and more as you go up to the ground, right? So you know the neutral plane at 205, right? This is 205. So you go down 205 and you go down here. So this will be your soil settlement, right? 1.2 or approximately 3 centimeter. So according to the neutral plane theory, your pile will deflect approximately 3 centimeter plus the elastic shortening, which is very small, you know, right? So for any practical purpose, your pile will settle approximately 3 centimeter. Okay, so and then after the placement of the embankment, so you need to what happens is that the contractor then will adjust the bearing of the bridge, you know, so it will make up this 3 centimeter. Right? They need to make some adjustment on the bearing so they can so that the bridge will sit at the right elevation. Okay, so the other thing is sometimes, you know, for the design of the pile, you know, typically, you know, you have this bridge, right? You have a pile cap or a single pile or pile group. Right? In this case, it's a pile group. Typically, you know, sometimes you want to do soil structure interaction analysis is preferred, right? In lieu of the fixed space. Typical practice is people assume a fixed space, right? So the bridge will be assumed, the bridge is assumed to sit on the fixed space, which is not true, right? In reality, that the pile cap or even the single pile will have some flexibility, right? So it's not fixed, you know. So typically you want to do soil sensor interaction instead of assuming a fixed space, maybe because it's more realistic. So then if you do that, then you need the stiffness metric, right, for this pile group or pile cap. So this is the program that we use, a program called FD multiplier, and the program will compute the stiffness metric for you. It is basically this one. So 6x6 metric for, you know, basically axial force X, Y, and Z, and the moment X, Y, and Z. So 6x6 stiffness metric. So you can use this stiffness metric, give it to the bridge engineer, and then he or she can use this metric to design the bridge. Right? So yeah, and the stiffness metric is used by the bridge engineer for structural analysis. One more thing I want to discuss is the strain compatibility. Okay? The strain or settlement that is required to fully mobilize tip resistance typically is a lot bigger than what is required for sub resistance. That in order to get full tip resistance, the pile had to move like maybe 5%, even sometimes 10% of the pile diameter. Where for subfiction, it takes just a little bit of movement to be able to get the full sub resistance. So there's this issue of strain compatibility because they don't occur at the same strain level. So you need to be careful, you know, you cannot just combine them because they will, most of the time, they will not occur at the same time. So what we do typically for surface limit or operational limit, we typically the load is smaller, right? We only use sub resistance. Tip resistance is not used, you know, because it's not fully mobilized. So we ignore them, we use only sub resistance. And for strong limit, we use 100% of sub and some fraction or some percentage of tip resistance, depending on how much your tip moves. If your tip moves a lot, you can use 100%. If your tip moves just a little bit, then you might want to use maybe 10% or 20%, you know. Obviously, 0 is conservative, but you don't want to do that. And for earthquake loading, for OBE, operating basic earthquake, typically it's a small earthquake. I only use sub resistance. I do not use tip resistance. And then for MDE, maximum design earthquake, I typically use both of them, 100% sub and 100% tip. Right? Because under the MDE, the pile is expected to move significantly. So you can have 100% of tip resistance. Okay, so that's all I have on the design side of the pile. Should I stop here and get question, or you want to continue? I don't know what time it is now. 7:15. It is okay to go a little bit over, Pak Jevan, or you have to. Pak Jevan? Hello? Anybody can hear me?
Ya, bisa diselesaikan aja, Pak Dario, sebelum
Okay.
nanti ke pertanyaan.
Okay. So that are the design, right? Design part, how to design the pile, give you, how you collect soil data, design part. But so the next part will be when you construct the pile, you need to verify, right, that your pile is good, right? You cannot just drill a hole, pour the concrete, and done. You need to make sure that your hole is good, your pile is good, it meets all the specification, the intended, purposes of your pile, right? You cannot just over. So I will talk about some of the verification methods we typically do. So verification method for drilled shafts, right? So we have quality check the quality of the pile. So first of all, you need to make sure your bottom is clean, right, before you pour your concrete, especially if you rely on the tip resistance. If you rely on tip resistance, then you want to make sure the bottom of the hole is clean before you pour the concrete. Secondly, you want to make sure that the hole is pretty constant all the way up, right? Not going up and down, but basically the hole should be more or less constant up and down, and relatively vertical too, right? You don't want your pile to be, at an angle like that, and then it's not the one that you design, right? So you want to make sure the shape is relatively good. And thirdly, you want to make sure that the concrete is of good quality, right? Because when you construct a very large diameter drilled shaft, you're talking about a lot of concrete, right? It's not like driven pile, it's only a little bit. You're talking about massive amount of concrete. So you want to make sure that you have a solid pile. There's no void, no anything, inside the pile, because that will affect your structural capacity, right? If you have a big void or big hole in the middle of the pile, so you want to make sure that your quality is good. So, and the second check will be capacity check, which you want to do the axial capacity check, and you also want to do the axial lateral capacity check. Right? So those are typical. You do this for any pile, not necessarily for the pile. So quality check, bottom condition. How to check bottom condition? We usually use what is the device called SQUID, shaft quantitative inspection device. Or we can use what is called MINSID, miniature shaft inspection device to check the bottom condition. Right? So for the whole condition of the hole, I typically use, what is called SHIP, right? Shaft area profile interrogator. So it's a device to check the whole condition. And for concrete quality, there are two, at least there are three methods, that I know, or that I use. Gamma logging, and secondly, cross-sonic logging, and also what we call 3D tomography. Using the CSI data, you create a 3D pile model tomography. Right? So this is an example of the specification of the drill shaft. Is telling you, that the bottom diameter should not be less than what you designed for, but can be a little bit bigger, no more than 6 inches. Measured in a direction. The verticality of the pile should be no more than 1 degree. Should be 1 horizontal and 100 vertical. And the bottom elevation should be plus minus 2 inches, no more than that. There's another qualification. Basically, telling you, this is typical specification for drill shaft, and then the bottom one is showing you the typical, bottom cleaning specification. Basically say that, no more than 50% of the base, you divide your area by 5 quadrants, and then no more than 50% of that quadrant or measurement should be, more than half an inch. That no more than 50%. And none of the debris should be more than 1 inch. This is very typical spec that we use in California. So I show you that this is approximately the device, the squid. I think this is the pedal that they push into the ground to measure the debris. Right? So we just showing you the typical. So remember I talked about dividing the whole thing into 5. So we divided the whole pile into 4 area and 1 in the middle. So 5 points. Right? This is the one that they did for this area and 1. So they took 3 measurements. Right? Each measurement, this is the debris thickness they estimated. So 0.14, 0.03, 0. So it's very, very good. Right? It's very clean. It's very clean bottom for this area. And then this is another example of they did the squid for this quadrant or this area. And again, this is the estimated debris thickness, 0.07, 23, 19. So they all meet the specification, right? So they're all good. So the bottom is clean, Well, they have to show that they have this value for all the quadrant, okay? Not only for the 2, but all 5. So again, and I just repeat you that example of the X7, that no debris should be more than 1 inch, and no more than 50% should be more than 0.5 inch. For the shaft, okay, this is the typical equipment that we use here, or at least on my project. I don't know. There are different equipment that you can use, but this is the one that we use. That's so what you get is basically the image of the hole. This is I think this is all like a sensor, camera sensor here. They can create this 3D, showing you the condition of the hole, right? This is, the length of the pile is about 140 feet. So it's what, like 50 meter, 45 meter, right? So the diameter is approximately 6 feet. So it's almost 2 meters. So example again, okay, this is the profile that they cut here between 2 and 6. They cut it here. This is the profile that they get from the device, right? So it's not that straight, right? Going down a little bit here. So it's not very, very nice. It's not very nice looking hole. This is another cross section that they cut, from this direction between 8 and 4, and this is pretty decent, a little bit at the top and a little bit smaller at the top, at the bottom. So that, and then measure the hole verticality. The red one is the approximately the locate, basically the pile, and the black is the one at the top. So you can see the eccentricity, right, between these 2 points. So here the verticality is 0.25%, right? Which is okay, because typically you want to limit the verticality to be less than 1%. So this, although this hole is not perfect, but I think meet the specification, so it's acceptable. And typically you also check, you can check with volume of concrete that you use, that the red line is the theoretical volume, the volume of the concrete that you need if you calculate it based on the hole. Nice looking hole straight up and down. This is the amount of concrete that you need, like 170 cubic yard, right? And the black line is the actual volume of the concrete. No, sorry. The black line is the volume that you estimated from the shaft, okay? From the diameter that you measure in the shaft device, right? So you can see here, what you're telling you is that the hole actually is the hole is bigger than what it should be. I want it here, but I get bigger hole. So it is maybe not that bad. Huh? You don't want to have a hole smaller, but it is bigger, maybe it's okay, as long as you don't pay for it. And this is also another check that you can do. The red line is based on the nice hole. So it's basically the same red line here. So based on the volume of the hole on paper. And the green is the actual volume of the concrete that you pour in. Again, you can see you actually use more concrete than what it should be. If you drill the hole very nicely, then perhaps your line should be close to the red, right? But here he's telling us that actually your hole is bigger, and therefore you use more concrete. It costs you more. So this is another check, check whether your hole is reasonable or not. Okay, now on the concrete quality. So typically this is the cross section of the drill shaft. Right? So you typically to do the test you have to install the PVC part, like a plastic part, so 2 in diameter inspection part. Total here you have a total of 6 here around the pile. So this is example of the PVC part you install around the pile. Right? So you can do 2 tests like so. It's the gamma logging is measured the quality of the tube, the quality of the concrete around the tube only. You cannot measure anywhere, just around the tube. And then the other one, the CSL, the sonic logging, cross sonic logging is measuring the quality across tube. So, for example, across this tube and this tube. So basically measuring the concrete quality here. So let's give you the, in California, you use test methods 233. They basically measure the density of the plot concrete. So this is this example result of the gamma. This is the plot of the deviation, density deviation from the mean. Right? If your concrete is good according to the spec, then the deviation will be 0, right? But if your concrete is less than that, the density is less than that, then you have a deviation, right? So the red line is the limit, okay? If your density deviation is more than the red line, that means that you may have a problem here. Your density is too low. Right? So you may have some issue with your concrete here. So this is the area of low density that could be avoided, could be some honeycombs. Basically it's telling you that you may have some issue with your concrete quality at different depth. So I'm not going to read this. This is just typical specification of how you define whether you have a problem or not. Like if you only have 1 point here, it may not be a big deal, but you have a cluster of points like here, then you may have a serious issue here. CSL basically is measure the pull arrival time. So basically you measuring the pull arrival ultrasonic pull from this point to this point, so across the pile. So it's basically using the arrival time, right? If your arrival is very late, it means that you have a void, right? If you have a void, then your signal cannot go very fast. It's late, right? So for example, this is the guideline that they give you, that if your arrival time is between 0 and 10%, oh, maybe you're good. But if your arrival is more than 20%, then you may have a problem here. You may have a problem with your concrete. So for example, at this point, you have a big arrival time here, right? Late arrival here, long arrival time. So this is between tube 1 and 7. So you and 7, so yes, that. So there's could be some anomalies here, right, on the concrete based on the arrival time. But there's another one. Okay, this one is taking from here to here, right? This one is measuring from here to here, small here. So again, you may have a, ultrasonic pull from here to here. You may have some issue here, maybe not that bad, but you still have maybe minor issue here. this location. That, so another test will be tomography. Sorry, I'm going pretty fast here. So basically, it's not a new test, but it uses the CRS data, and it will create a 3D PAL profile. So basically, it measures the effective area to the area with acceptable, arrival time. So basically, it uses the CLD data and create this 3D PAL profile, and then you can cut the PAL at any depth. This one is at depth of 9 feet. This one is at 9.5 every 5 feet, half a feet. This one is at 10 feet, and this one is at 10.5, and so on, right? So you can have a profile at any depth that you want to cut. You just need to tell the program, where to cut. So again, this for example, this guy, the one at depth of 10.05, you see a big red area here, right? So this could be showing you that this may be a problem here. You may have a problem at depth of 10.5 feet. Right? So, and this is consistent with the result of the CSL, right? The one that I showed you before. You may have a big issue here, and maybe a little bit, issue here and there, but this could be the biggest area where you have a void. Should I go with this or just stop here? Maybe I think we are running out of time, but should I just stop here? already.
Ya, saya kira waktu kita sudah habis, Pak Dario.
Masih ada, cuma untuk capacity untuk lateral dan axial. I don't mind if everybody okay. I can spend maybe another 10 minutes to get it through.
Oke. Ya, silakan.
Okay.
Ya.
Okay. I go quickly. So basically, your axial capacity, right? You want to test your PAL for compression and tension, and also for lateral capacity, or you want to check the response of the PAL, right? So for axial capacity, typically, with drill shaft, the capacity is very large, right? So nominal capacity or large diameter drill shaft is typically very large, and so conventional test by applying load at the top, load may not be practical, or even sometimes it's not possible because the load requires so high. Right? So what we typically use is we use what is called O-cell or O-stable cell as the alternative during the test. Basically, you have a PAL here, and you put like a load cell here, loads here at certain depth, and then you basically inject test the PAL. So you put the pressure here, so the top part will go up, the bottom part will go down, right? By directional load. Right? So when you do that, hopefully you'll be able to use smaller load and be able to test the tip resistance. You will get the result for tip resistance. So O-cell, this is typical. You put the cell here in the middle somewhere, so this is the top PAL, this is the bottom PAL, this is the load cell. Right? So again, so this is the top and bottom, you put the load cell here. So the pressure that going upward will be received by the width of the PAL and the size resistance, right? And the pressure that going down will be received by the tip resistance and the side resistance. Right? So basically, you push the top up, you push the bottom down. So the key is how where to locate the cell, right? So you need to calculate based on your data where you're going to put the cell, so that there is a likelihood that the upper and lower part of the PAL will fill at the same time. But it's easier said than done. Typically you will not be able to do it, but you do your best. Try to predict, where is the location of the load cell. So instrumentation, typically you put the strain gauges along the PAL to measure the strain. So when you get a strain, you get a stress, and then you can estimate the curvature and the deflection. Right? So you install a series of the strain gauges. So this is the test ASTM. You wanted to test, this is the test ASTM, and the test, you increase the load slowly and then reloading. Right? So this is the plot between axial load and time. Right? So this is the plot between the time and the displacement. The blue is the one at the top move, and then the yellow is the movement for deflection, the one on the bottom, right? The bottom part. So when you plot between load and displacement, this is what you get. So the top pile moved less than 1 inch, but the bottom pile moved 7.6, which means that the tip resistance is fully developed, right? The tip resistance. So this is the measurement on the strain gauges. This is the top of the pile. They measure the displacement and unit shear. This is what you measure at the bottom. Zone 1, zone 2, right? This is so it's showing you this is not quite failed yet, almost failed, but on the bottom part is completely failed already. Right? This is what you have a displacement or end bearing, the tip. When you do the test, you want to use the result of the test to verify your design, right? Or to calibrate your design so you have a better prediction of your pile capacity. So this I'm showing you, that the beta, remember the beta value, the sub resistance. The red one is the value that we used originally based on the ASTO, the red one. And the dot is the result for the 2 tests. We did 2 tests, 2 load tests. So dot are the one for the, so in general, they are quite consistent, right? They are not that bad actually, but we finally try to optimize the design by using the green line. The green line is the adjusted or calibrated beta value for our pile. So we recompute our pile design using this green line to estimate our capacity. Okay. Same thing with toe resistance. The red is the one that we use from the ASTO, and the dot are the one that we cut from the test. So we decided just, maybe this is good enough. We can go a little bit higher, but we decided not to do that. Okay, so the green line again is updated value, and the one is also the one that we use to cap 50. Lateral load, is same thing. Right? You have this is the pile that you want to test. This is the reaction pile, right? Basically to test the deflection profile. So this is the figure showing you the load test and a lot of cable coming up. So this is the standard ASTM. Just showing you, this is the load cell. And again, this is showing you the load and time or lateral load, and this is the displacement. The top of the pile displacement. This is the test shaft, and this is the reaction shaft. And if we plot load and displacement, this is what we get. Test pile, the reaction pile. Right? So the test pile moved approximately 3.75 inches. This is showing you the profile from different loading states. Ideally, you want to put the inclinometer in the middle of the pile, so you can measure directly the profile, right? The inclinometer, you can measure directly the pile profile, but we didn't use that. So we use the strain gauge data to estimate the profile, which is less accurate. Right? We can use this equation to estimate the rotation and displacement. But again, as I say, it's not very accurate. I think if you want to have accurate, you have to use inclinometer. Okay, so similar to the Excel, we want to calibrate our design based on the test result. So it is showing you the solid line is the one that we use for the design based on the L-pile. Oh, sorry. The test line, red test line is the one we use for the design. The solid line is the one that the solid line is the one that we get from the test. As you can see, the shape is a bit different. It's very, I don't think we can predict this double curvature. So we end up using this solid test line for our design. It is not exactly match the test result, but somehow capture the overall overall profile. Okay. So useful design is this one, right? This is the pile. I think that's it. I'm sorry, I think I had to run it through fast. Any question?
Baik, terima kasih Pak Dario. Presentasi yang sangat menarik. ada soil investigasinya, ada desain pondasinya, dan juga ada verifikasi. Jadi sangat lengkap ya. Sekarang kita ada waktu untuk tanya jawab. Yang di chatting room sudah ada tersedia 6 pertanyaan. Nanti silakan adik-adik mahasiswa yang di ruangan ini juga bisa bertanya. Kita masih ada waktu sekitar setengah jam ya. Baik, Pak Dario, itu ada satu pertanyaan yang bisa ditampilkan di share screen. Oke, ada pertanyaan pertama, Pak Dario. Yeah, in surprise limit state for determining the short-term settlement ini sama lot transfer method yang direkomendasi oleh ASTO. Bagaimana pengalaman Bapak untuk lot transfer analysis yang diharuskan ini? Silakan Pak Dario untuk pertanyaan pertama dulu.
Ya, saya akan nggak bahas mengenai settlement, tapi biasanya kita pakai program called shaft program. So I understand the program will give you the TC curve, the TC curve that you can use to estimate your short-term settlement. So we use that, I think we use that. So I don't know, is there any issue why you will not use that from your program? Or for us, is the TC curve, we can get it rather easily from the program. TC curve, or is that your question?
Siapa Pak?
So the answer to that, yeah, we use the load transfer methods to estimate our settlement.
Baik, untuk pertanyaan kedua, yang di ASTO dia menggunakan pendekatan LRFD, sedangkan Indonesia ASD. Bagaimana pengalaman Bapak untuk penerapan ini di desain geoteknikal?
Saya sih bergerak di infrastruktur. Saya nggak ada pengalaman di gedung, misalnya gedung 10 lantai, 20 lantai. I don't have the experience, but from my experience in infrastructure, like bridges, things like that, or airport or whatever, typically we use RFD. I understand that most of the design, like foundation, like isolated footing, thing like that, we still use allowable, right? Even us to have very, very minimal guideline on that one. So what is the main challenge for applying RFD approach in geotechnical? I don't see any challenge, because ASTO, if you design a bridge, they give you everything. They give you load factor, they give you resistance factor. So all you need to do is you just have to select the one that is appropriate for your project, right? In Indonesia, as I say, that the load factor and resistance factor that you should use ideally should not be the one that in ASTO, right? Because those in ASTO are based on the United States local practice. May not be the same with Indonesian practice. I don't know. So it could be better, could be worse. I don't know. But if you don't have the data, then typically you will use the same factor, right? In US, or I don't know, in Japan. Does Japan use the RRD or?
Oke, mungkin ada yang dari ruangan ini, silakan ada mahasiswa yang mau bertanya, boleh maju ke depan ya. Ya, silakan. Pasal malu-malu anak UPH. Ayo bertanya.
Ya bisa bahasa Indonesia oke lah. Saya usahakan jawab bahasa
Indonesia boleh, bahasa Inggris juga boleh. Ayo. Ayo Nehemia atau siapa? Biasanya Nehemia banyak pertanyaan. Atau Deril sila, please Deril. Ayo Deril. Kalau enggak Daniel, ada pertanyaan Daniel. Daniel Witono atau Daniel Ricky juga boleh. Ada atau masih berpikir-pikir dulu ya? Oke, kita lanjut dulu ya. Nanti harus ada pertanyaan dari kelas ini ya. Ya pertanyaan ketiga ini mengenai file ini, Pak Dario. Bagaimana pengalaman Bapak lagi tentang profile formulanya menurut literatur yang dia asto. Bagaimana juga menghitung bearing capacity-nya nanti, Pak Dario.
Ini nomor 3 ya, prefabricated part for pre-ball hole.
Ya, silakan Pak Dario.
Ya, I prefabricated part, so you drill a hole, you insert your prefabricated part, and then you fill the annulus with some kind of cement. Such a case, can you? I think to compute the geotechnical capacity, I think you can use it for geotechnical capacity, right? Obviously, the structural capacity of the pile will be very different. But to compute the site resistance and perhaps the tip resistance, I don't see any issue there. I never did it before, I don't know. Nggak pernah saya desain. Biasanya di sini kalau lubangnya lebih besar kita fill dengan gravel ya, atau sand atau gravel, not cement.
Oke, langsung ke pertanyaan keempat lagi. Bagaimana menentukan panjang tiang berdasarkan displacement lateral? Ini Pak Dario, kriterianya bagaimana? Atau itu ada sampai 1 inci atau bagaimana? Yang nomor keempat.
Ya, kita tetap harus memenuhi desain kriteria. Kalau desain kriteria misalnya tidak boleh lebih dari 1 inch, kita make sure bahwa itu nggak akan lebih dari 1 inch. Cuma untuk menentukan panjang tiang untuk lateral load, kita biasanya lihat kalau memang seperti yang saya tunjukkan, kalau pahatnya sudah nggak bertambah, berarti nggak ada gunanya kita perpanjang lagi tiangnya. Kalau 30 feet displacement-nya itu sudah stabilize, kita nggak perlu memperpanjang tiang kita 40 atau 50 ya. Tapi the displacement still harus memenuhi desain kriteria. Kalau desain kriteria nggak boleh lebih dari 1 inch, ya kita make sure tidak akan more than 1 inch.
Oke, ayo ruangan ini juga biar nggak ngantuk, silakan untuk bertanya. Sudah dapat pertanyaannya? Belum juga. Ayo, silakan bertanya. Yang di belakang ini sudah pondasi dalam loh ini ya. Anak, ya sudah ya.
Jivan, boleh bertanya?
Ya.
Ya silakan. Kalau ada dari Zoom juga silakan ya, langsung ya.
Baik, Pak Dario, salam kenal. Saya Aksan, Pak, dari Jakarta.
Selamat pagi, Pak.
Selamat malam, Pak. Nice to see you.
Di sini Oke.
Pak Dario, thank you untuk great presentation-nya. Saya mau bertanya mengenai common practice gitu ya. Apakah memang di US itu sudah menjadi satu common practice untuk melakukan berbagai macam instrumentasi yang tadi saya lihat gitu ya. Kayak misalnya mencari load transfer sebagai pembuktian, berarti kan kita sudah melakukan pemasangan strain gauge, extensometer, dan kemudian untuk memverify gitu ya, bagaimana kondisi lubangnya. Saya lihat tadi kan kita ada menggunakan speed, kemudian ada menggunakan shape atau anything gitu ya. Bahkan lateralnya pun kita instrumen gitu. Apakah itu sudah menjadi satu common practice atau bahkan sudah menjadi satu standar yang diwajibkan gitu? Sementara itu sih pertanyaan saya.
Ya. Kalau
Thank
untuk
you,
saya banyak mengerjai infrastruktur, jadi proyek-proyek basically pemerintah punya. Jarang sekali saya ngerjain proyek untuk private. No, karena yang bangun jembatan apa itu kan bendungan segala kan pemerintah. Untuk pemerintah biasanya diwajibkan, apalagi untuk proyek-proyek yang cukup kritikal. Jadi minimum harus ada tes setiap, kalau nggak salah untuk proyek ini misalnya tiap 50 pal, 500 pal, 50 pal harus ada satu tes pal. Dan tes palnya harus komplit axial, kadang-kadang tension juga, ada lateral. Jadi to answer your question, I think in private, I don't think they require you to do that, but for government funded infrastructure, yeah, I think this most of the tests are required. Seperti yang tes yang tadi CLL, shape, bottom, itu di require sama Caltron. Caltron itu adalah apa? California Department of Transportation ya, seperti PU-nya di Indonesia, tapi ini untuk California. Dia
DOT gitu ya, Department of Transportation-nya gitu ya.
Ya. Di Amerika kan tiap state ada sendiri-sendiri. Kalau di California kita pakai Caltron. Caltron itu require you to do the test. All those tests ya, squid, lalu shape. Bahkan yang go ahead.
So that means it's required not only a common practice in some states in America, right?
Yeah.
But not in all states.
Well, most likely all states. Most likely all states. Typically, Caltron is always at the front. So other states typically just copy what Caltron is doing.
It's like a golden standard used by all states in America.
Yeah.
Okay. Thank you for your explanation. Thank you.
No problem.
Ya, terima kasih Pak Aksa atas pertanyaannya. Kita masih ada 2 pertanyaan lagi Pak Dario. Ya, nanti kalau ada lagi masih ada waktu sampai jam 10 ya. Korelasi. Ini korelasi beban dengan displacement ini Pak Dario untuk QU kapasitas ultimate-nya. Itu bagaimana?
Correlation of load. Saya nggak terlalu get it. Maksudnya korelasi load. Ini maksudnya
berdasarkan beban dan displacement, kita bisa tentukan nggak kapasitas ultimate-nya untuk tiang yang berdiameter besar ini gitu.
displacement, maksudnya axial load-nya.
Aksial
Maksudnya displacement maksudnya.
Ya.
Ya, seperti yang saya tadi tunjukkan kan ada plot antara load and displacement. Kita kan bisa lihat untuk load-nya ultimate capacity-nya sampai di mana, no? Seperti tadi yang saya tunjukkan yang terakhir hasil dari tes itu kan displacement versus load. So at certain displacement value, then the load will become stable, right? Almost horizontal. Itu kan ultimate capacity-nya. Seperti dengan shallow foundation, right? I mean, the capacity of the foundation is typically defined where the load is, where the displacement reach certain value, right? So when you see, kalau kita lihat plot antara load dan displacement, biasanya kan seperti curvature lalu flat. Jadi ultimate capacity-nya corresponding to the flat part, right, of the curve. Yeah, I answer that. Mild pile diameter is large.
Ya. Ada satu lagi Pak Daryo, bagaimana kondisi tahanan friksi pada tiang yang dikerjakan dengan metode pre-boring? Apakah daya dukung lateral tiang akan berkurang dan bagaimana penanganannya?
Gimana kondisi tahanan friction pada pile yang diberikan? Besok kan pre-boring ya, kita drill hole first, kan? Kita pre-drill hole-nya, kan? Lalu baru kita, biasanya hole-nya itu kan harus di-stabilize ide pakai bentonite slurry atau polymer, kan? Biasanya kalau pakai bentonite slurry itu friction-nya kecil sekali. Saya pernah coba dua tes hampir sama. Satu pakai bentonite slurry, satu pakai polymer slurry. Friction-nya beda jauh sekali. Yang pakai bentonite itu jauh lebih kecil daripada yang pakai polymer, synthetic polymer. Saya nggak ada data. Mestinya saya bisa tunjukkan perbedaan antar. Jadi, I think untuk answer question-nya, ya ada bedanya tergantung sama slurry yang dipakai, ya.
Pak Daryo, maybe the question related to driven piles, because usually when they have a driven piles with a sand lens, then they need to pre-bore the sand lens.
Oh,
Thank you. Sorry.
ya, sure. Di Altran juga ada spesifikasi kalau kita pre-drill hole, dipikirnya pre-drillnya kan lebih besar, ya, lebih kecil sedikit ya. Lebih kecil sedikit dari tiangnya, kan? Lalu tiangnya di drive right through it. Yeah, well, no. Yeah, obviously, yeah, you have to have some reduction, right, in the friction. Misalnya tiangnya 12 inches, biasanya pre-drill hole-nya kan lebih kecil, 10 inches atau 11, right?
Oke, baik. Ya, jadi mohon maaf jika masih ada beberapa pertanyaan karena waktu itu kita sudah selesai. Saya kira juga di sini nggak ada yang bertanya lagi ya, di ruangan ini nggak ada. Baik, dengan demikian kami ya, jadi mohon bagi semua peserta untuk mengisi link absensi karena nanti itu data kita untuk bisa membuatkan sertifikat ya. Jadi kita berikan aplaus dulu sama Pak Daryo.
Oke, thank you.
Terima kasih Pak Daryo dan juga ICETS-nya. Semoga kita akan bisa bertemu kembali di kesempatan-kesempatan berikutnya. Tetapi mungkin Pak Daryo ada mau sampaikan sekaligus sebagai ya apa yang Bapak bisa sampaikan, silakan Pak Daryo.
Ya, saya kan di sini saya mewakili ISTESNA. No? Tadi seperti Bu Nani yang jelaskan bahwa salah satu daripada program kita adalah kerjasama atau koordinasi dengan lokal university di Indonesia untuk apa tukar pengalaman gitu ya. Karena seperti Bu Nani tadi bilang, anggota kita sebagian besar practitioner seperti saya, tapi ada beberapa yang di akademika yang mengajar di sini. Jadi banyak topik yang kita bisa cover. Background-nya saya di geotech sama seismik, tapi banyak anggota yang di bidang-bidang lain, struktur, pengairan, CM. Ya, dan juga kita ISTESNA ada webinar tiap bulan. Lalu topiknya itu berganti-ganti. Topiknya macam-macam, teknik sipil. Jadi kalau bapak-bapak dan ibu-ibu mau ikut, bisa ngirim email ke saya atau ke Bu Nani, kita bisa tambahkan di distribution list-nya. Untuk minggu depan ada satu yang membawakan, kebetulan saya lagi, topiknya development of seismic design, facility. Yeah. Development of seismic design ground motion. Oke, itu aja Pak.
Ya, baik Pak Dario, terima kasih banyak dan juga kami berterima kasih banyak juga bagi semua peserta. Semoga kita bisa bertemu kembali di kesempatan berikutnya. Mungkin 1-2 minggu ke depan kita masih ada lagi beberapa pertemuan-pertemuan dengan kuliah umum bersama ICES-nya. Baik, terima kasih dan juga kami berterima kasih untuk adik-adik mahasiswa yang ada di ruangan ini. Dengan demikian berakhir sudah acara webinar kita pada pagi hari ini. Terima kasih, Tuhan memberkati.
Oke.
Terima kasih Pak.